Every minute, your heart pumps roughly 5 liters of blood through thousands of miles of vascular tubing. But the entire purpose of that massive network relies on what happens at its absolute smallest endpoints, where red blood cells literally squeeze in single file to deliver oxygen to your tissues. This microscopic terminus is the capillary bed. It is the only place in the entire cardiovascular system where gases, nutrients, and fluids actually cross the vessel wall. To keep tissues alive, the system faces a constant physical paradox. It must push fluid out of the blood to deliver nutrients, but it must also pull that exact same fluid back into the blood to prevent you from losing your circulating volume. This diagram outlines the overarching anatomy of that exchange site. On the left side, blood enters from a high-pressure muscular arterial, flows through the branching capillary network, and drains into a low-pressure venule on the right. Notice these rings of smooth muscle acting as valves at the entry points. These are pre-capillary sphincters, and they constantly contract and relax to control exactly how much blood enters this network, based on what the surrounding tissue demands. Managing the fluid across this network is not a passive process. Fluid homeostasis is a strict mathematical balance dictated by 2 factors: the physical structure of the vessel walls and the competing biophysical pressures pushing and pulling across them. If any variable in this equation breaks, fluid immediately accumulates in the surrounding tissues, causing severe swelling, known as oedema. Without perfectly balancing this microscopic push and pull, your tissues would drown in their own fluids, while your blood volume plummeted, leading to total cardiovascular failure. Before calculating the pressures moving fluid, we have to establish what can actually pass through the capillary wall. Permeability is governed by the physical gaps between the cells. This comparison illustrates 3 distinct capillary classifications. On the left, continuous capillaries use tight junctions, allowing only small molecules through. In the middle, fenestrated capillaries feature microscopic pores for rapid filtration. On the right, sinusoidal capillaries have massive gaps, allowing large proteins to diffuse. Regardless of the physical structure, lipid-soluble molecules like oxygen and carbon dioxide constantly pass through all these cell walls via free diffusion. The anatomy dictates the capacity. The liver can only export large proteins because its local capillaries are built with specific, wide openings to accommodate them. Knowing the physical limits of the walls, we can map the invisible physical pressures that force water through them. These competing fluid pressures are collectively known as the Starling forces. This diagram illustrates the pressure vectors acting on the fluid. First is hydrostatic pressure, the mechanical force of water moving down a gradient. Capillary hydrostatic pressure, PC, provides the intense outward push into the tissues. Opposing it is interstitial fluid hydrostatic pressure, pi, the minor resistance pushing back. Second is oncotic pressure, an osmotic pull driven by large proteins. The dominant inward pull is blood colloid oncotic pressure, pi-c. Trapped plasma proteins exert a massive pull, dragging water back into the blood vessel. Finally, the interstitial fluid oncotic pressure, pi-i, exerts a slight outward pull. Fluid exchange is not a conscious cellular decision. It is purely the blind mathematical sum of these 4 competing physical vectors pushing and pulling against each other. To determine whether fluid actually leaves or enters the blood, we calculate net filtration. This equals the total outward push minus the total inward pull. Starting on the high-pressure arterial end, the outward forces are 30 minus -3. Inward forces are 28 minus 8. The hydrostatic push easily overpowers the oncotic pull. The math yields a net filtration of positive 13 millimeters of mercury, driving bulk flow out of the capillary. But as blood travels further down the microscopic tube, friction and fluid loss cause the internal hydrostatic pressure to plummet. At the venule end, we see a crucial shift. Outward hydrostatic pressure drops to 10. However, the inward oncotic pull remains locked at 28 because large proteins cannot escape. The venule equation yields a net force of -7 millimeters of mercury, flipping the gradient entirely and driving fluid reabsorption. Notice the mathematical asymmetry. We had a positive 13 pushing fluid out, but only a -7 pulling it back in. The cardiovascular system's reabsorption mechanism is mathematically imperfect. It leaves fluid behind in the interstitial space with every pass, requiring a secondary rescue system to prevent swelling. If fluid is constantly left behind in the tissue space, your limbs should be steadily swelling like balloons throughout the day. This diagram introduces lymphatic capillaries, a blind-ended drainage network interwoven with tissue cells. They act as a one-way vacuum, sweeping up excess interstitial fluid and escaped proteins. At rest, roughly 100 milliliters per hour is continuously routed back into systemic circulation. Healthy tissues are maintained by two distinct parallel systems: the mathematically leaky cardiovascular delivery network and the relentless vacuum of the lymphatic drainage network. We can prove this biophysical model by looking at what happens when it breaks. Consider a 15-year-old sharply spraining an ankle during a football game. The acute physical injury triggers an immediate biological cascade. The body initiates a local inflammatory response, causing rapid vasodilation to flood the area with blood. Inflammation widens capillary junctions, allowing plasma proteins to escape into the interstitial space. This mass exit causes the blood colloid oncotic pressure's inward pull to collapse. Without it, the venule fails to reabsorb fluid, driving non-stop outward filtration across the capillary bed. This massive fluid shift outpaces the drainage capacity, instantly overwhelming the local lymphatic system. The resulting swollen, puffy ankle, clinical oedema, is the macroscopic symptom of microscopic Starling forces failing under the stress of trauma.